x to 2.6 looks like. And as the order, I'll decrease the order to show how much it increases in complexity. So this is what happens when I increase it from 2.6 to 1.8. It becomes when I raise it to different exponents, it changes the way it compresses onto itself. So let's assume that the valence waveform of radon was cosine x to the 8th complexity. This is what it would look like. And it turns out that as you move leftward, that although radon is the one most to the right of the periodic table, atoms with 8 valence electrons have very complex valence complexity, and as you move down the table, as you move leftward from the on the table, they become less complex. So let's demonstrate this. These atoms have x to the 5th valence complexity. These atoms have x to the cubed valence complexity. It looks like the same thing. These ones have x to the squared valence complexity. So this one is much more coherent and ordered than the x to the cubed valence complexity. So when you move down to this atom, you get a very neat and ordered valence complexity. But hold on, wait a minute, there is a problem. This element has a constant 10x complexity. You can also do this with tangent. So I'm going to switch this to tangent. It has a constant tangent x complexity. It has no ability to reason beyond the bounds of these curves. That's what that means. So it turns out that the atom just left from it has 1 valence electron most of the time, but sometimes it can have 10 to the 18th valence complexity. And this is what that looks like. And when we switch back to cosine, this is what that looks like. Well, it looks similar to others of previous ones, but it's actually very, very complex. So how do I make it longer? So for just a few milliseconds, a platinum atom can assume this shape and take on the forms of nearly all the other previous shapes, and then go right back to being this shape almost instantly. I'm going to increase this back to 18, and I'm going to include tangent x. That's what it looks like. So for this reason, it not only has a polymorphic complexity, but it can sort itself back into a predictable pattern. This is why it is important to employ platinum in place of uranium for purposes of energy production, since it is far more capable of intelligent computation of any other atom besides element 110. This is a simple polynomial for the valence pattern. If you want to do plus the other elements, it would be plus some quotient c, and I can't determine c, x raised to the 32nd, which is the amount of electrons in its next shell. So if I remove the c, these would be equivalent, but technically this is far weaker than this one, since this one is at the surface, and it looks like that. So that's technically more similar to what it looks like, but for my purposes, we're only focused on the valence electron configuration. Out of concern for employment of uranium as a viable power source on the psyche of all people who are affected by it one way or the other, and the interest of seeing a more stable element work in this function, I'm proposing a very simple modification of a device that is present in almost all microwave ovens into a platinum decay looped harmonic resonator. It features 4 lobes containing one isotope of platinum 195, but alternates the different atoms that they each isotopes that they each contain. When the lobes are heated to sufficiently high pressure and temperature, the waveform of either isotope is played to the chamber of the other isotope at a specific amplitude, thus causing one isotope to become the other. So my analogy is, if you imagine a bunch of wrecking balls clustered together, 195 wrecking balls, and you take a crane claw and pull one wrecking ball out slightly. It takes a lot of energy to pull it out, and then due to the high energy of the strong force, it slams back in and pushes another one out the other end, and it just keeps doing that over and over and over, creating a lot of energy in a sort of feedback loop. This process emits more energy as it accelerates. So you can imagine 4 samples of platinum doing that at the same time, and the power is fed through a feedback loop until it passes through pressure forged platinum glass out into other power receivers and ambient air. This idea is a very simple concept that relies on the loop of 2 stable isotopes, 194 and 195, rather than chains of many very unstable atoms in order to produce power and efficiency. Power and efficiency because there is no loss, there is no waste. When the reaction cools down, all you should get back is stable, harmless platinum 195. There is no proliferation. These are the 4 samples that will work for as long as the generator will run, and they can move and they can be smelted down in another generator. It has the most complex elemental waveform of any other particle in the periodic table, which makes it a very, very highly coherent particle that can still run computations of of the order of the 18th order, x to the 18th. Let's look at uranium again. When uranium is not jumping in and out of existence like it usually does, it has a constant complexity of x squared to x to the 4th. See, look. Otherwise, the lines are very neat and ordered and parallel. To the 4th. They're more jagged here. And x to the 18th. So we can do a much simpler calculation of 18 divided by 4. In fact, no, 18 divided by 2. And we can say that, 18 minus 2. And we can say that platinum has x to the 16th times more complexity in its sentient behavior than something like uranium.